Welcome to 10.5, Day 1 Notes, Binomial Theorem and Binomial Expansion. The learning target for this lesson is that you will be able to use Pascal's triangle to write binomial expansions, that you can use the binomial theorem to find coefficients of specified terms in binomial expansions. Those are learning targets for Day 1, and then we're also going to be looking at binomial theorem to write binomial expansions. So, you were asked to do this after the quiz, to take the time to actually expand these. Anything to the 0 power is 1, anything to the first power is itself. You know how to square this, you just expand and then you distribute. And so this is what you got. For this one, to cube it, you've already got the squared answer here. So you take that and just then distribute in the a plus b. And you end up with this expression. And you continue this pattern up to the fifth as you were asked. You should notice some patterns. You should have made some observations about what's happening to the exponents on the first variable, a. It's going down by 1, and then it's a to the 0, a cubed, a squared, a to the first, a to the 0. A cubed, a to the fourth, a cubed, a squared, a to the first, a to the 0. And also for the variable b, it's actually decreasing from right to left, or rather increasing from left to right, starting as b to the 0 here, b to the first, b squared. B to the 0, b to the first, b squared, b cubed. I prefer to go from left to right, b cubed, b squared, b to the first, b to the 0. You may have also noticed some patterns with the numbers. In fact, this should look very familiar to you, particularly if you went through and looked up, because perhaps you don't remember it from Algebra 2, Pascal's triangle. Now there are many uses for Pascal's triangle. In fact, we use it to do a number of things, including combinations. When we're doing probability, it's possible to use them for combinations. In fact, we're even going to do use the combinations to help us do some problems when we find binomial coefficients in this lesson. The first row of Pascal's triangle is row 0. Gee, that's interesting. It matches up to a plus b to the 0. Row 1 is 1, 1. Oh, that's interesting. That's the coefficients on here. Row 2 is 1, 2, 1. Again, the coefficients on the binomial squared. Notice this was a binomial whose coefficients started out as 1 and 1, though. So that's why we're seeing the same numbers up here that we see in Pascal's triangle. Had we started with a coefficient of 2 and 3, we wouldn't have 1, 2, 1 as our coefficients. We would get something larger than those values. But there's Pascal's triangle, and to obtain it, we can start with a 1 here, and 2 1s. It actually starts with a triangle of 1s, and then to get the next row, you put a 1 on the outsides, and you add the 2 numbers above to get the number in the middle. Then I add these 2 numbers to get a 3, and I put 1s on the end. I add these 2 to get the 4, these 2 to get the 6, these 2 to get the 4, and put 1s on the end. These 2 to get the 5, these 2 to get the 10, these 2 to get the 10, these 2 to get the 5, and put 1s on the end. And so on and so forth, and I just keep going down with this to get however many of rows I need of Pascal's triangle. Pascal's triangle goes on infinitely. Yes, one of the things you might have noticed about the triangle, just as you might have noticed about these up here, is that the outsides are all 1, the outside coefficients. This row right here happens to be all of the natural numbers, the counting numbers from 1 up. There are other patterns in the triangle. Also, you can, actually that's a column. We would call this a column. This is called column 1. This is column 0. Column 2 goes this way. Column 3 goes this way. Column 4, and so on and so forth. And you're thinking, well, it has less and less numbers. Not really, because it would go down further into the triangle as we continue the triangle. Yes, it does have less than the previous one, but the numbers don't stop here. They keep going down with other rows. Well, we're actually going to use Pascal's triangle to help us with some binomial coefficients. we can actually use Pascal's triangle to help us find the binomial coefficients. And it will actually help us to generate binomial expansions without having to sit there and take the tedious steps to distribute a plus b to itself 8 times. So when I go to do this, I actually want to have Pascal's triangle handy. I'm actually going to pull it up on the screen for us so that I don't have to write it all out here. You already have it on the front side. So we're going to get Pascal's triangle. And where are we? I want, this one's fine. No, not very good. Let's go with this one. It looks nice and crisp. Close enough anyhow. All right, that'll work. And I'm just going to put that off to the side here. And I'll open this back up. So as I go to do this, let me just extend this window a little bit. I actually want the 8th row. This 8 tells me, and if you look back at the first page, when I look over here and I had b to the 0, the answer was 1. It came from the 0th row. B to the first was 1a plus 1b. That was row 1. A plus b squared was a squared plus 2ab plus b squared. So the exponent that we see right here corresponds with the row of Pascal's triangle. So when I have an exponent of 8, I need to use row 8 of Pascal's triangle to start off the problem. However, I also need to be aware of what the coefficients are on the a plus b. And if this is negative, make it a plus the opposite of whatever number's in front of b. We're going to do a simple one with letter A, and you'll see how it matches up specifically to Pascal's triangle. And then we'll look at what happens when we have number coefficients and eventually negatives. We may change this to a minus 3. So let's take a look at this one. I'm going to go to row 8, and I'm going to start, and I'm going to leave lots of space between the things that I use from row 8. So there's row 0, 1, 2, 3, 4, 5, 6, 7, 8. Here is row 8 of Pascal's triangle. It is 1, 8, 28, 56, 70, 56, 28. Shoot, I'm going to run out of room. 8, and 1. Now the reason I left space there is because I have these next to it. And so let me just make sure this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. All right. Now our first term is going to include A and B. Actually, every term to start will include A and B as we begin the problem. So I'm just going to go through real quick and put an A and a B next to each coefficient term. Well, we saw in our pattern on the other page, let me go back to it, that this right here, for a fifth, raising it to the 5th power, the a's went down by a degree. They started at the highest degree, a to the 5th, then a to the 4th, 3rd, 2nd, 1st, and a to the 0, which is why we don't see it there. It's really a 1 hidden in through multiplication. And b's actually either count up, starting at 0 from left to right, or as I prefer, from the highest exponent on the right, counting down. So on mine, I'm going to have a, this is going to be to the 8th, because my highest exponent for a is 8, then 7, then 6, then 5, 4, 3, 2, 1, 0. a to the 0 really becomes 1. So this is 1 times b to some power. Well, it actually is b to the 8th, because again, this is row 8. We're raising it to the 8th power. The highest exponent on b, when it's expanded, will be b to the 8th. So this is going to be b to the 8th, b to the 7th, b to the 6th, b to the 5th, b to the 4th, 3rd, 2nd, 1st, and 0. B to the 0 becoming, again, 1. So it's just 1 times a to the 8th. So I got my exponents from my highest to lowest, going left to right for the first term, and the second term of the binomial going from right to left, starting at the highest on the right and going down to the left to 0. Now, if there was a number in there, and there will be on this, we would actually have to raise that number to the 8th power, and this one to the 0, that wouldn't matter. The number in here to the 7th, the number in front of the b, the coefficient in front of b would be raised to the 1st. We don't have to worry about any of that, because I don't have a coefficient on a or b, it's just a and b. So this term right here simplifies simply to a to the 8th. This one to 8, this will be a plus sign between these, plus 8a to the 7th b, plus 28a to the 6th b squared, plus 56a to the 5th b cubed, plus 70a to the 4th b to the 4th, plus 56a cubed b to the 5th. And I'm going to do a line here so I don't confuse the work that I have shown with my answer. Plus, I just did this one, 28a squared b to the 6th, plus 8ab to the 7th, plus b to the 8th. There is my final answer. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 terms in it, because there were 9 elements or numbers inside row 8 of Pascal's triangle. And that's what it would expand to. If I were actually to take this and multiply a plus b times a plus b and do that 8 times. So this, even though this involves some work and knowing the trick, it does actually save you time to do it this way than to expand it by hand. Expanding it by hand is cumbersome and it's more likely for you to make arithmetic, or actually, yes, calculation errors, arithmetic mistakes. In this case, my value for a is 2x, is my new a. My value for b is 3y. So when I have it written out like I have above, because it's not just an a anymore, it's actually 2 times a variable, I have a coefficient, that coefficient is going to have to be raised to the exponent before I multiply things together. But it's going to start with the same setup. Going to row 5 of Pascal's triangle. So row 5 of Pascal's triangle, there's row 0, 1, 2, 3, 4, 5 is right there. So that means I'm going to start with a 1, a 5, a 10, a 10, a 5, and a 1. And I leave a little bit of space there because I'm going to need space to calculate things. Each of these will be separated by a plus sign, or sometimes a minus sign if we have a minus in there. We'll deal with that at the end, though. We're actually going to change the next problem. So right now I'm going to make this my 2x. In front of every coefficient, I'm going to put a 2x, which was my term for my a. And then next to that, I'm going to put 3y in place of what would be my b. And I don't need to see Pascal's triangle anymore. I actually could have generated the first 5 rows quickly. I just didn't feel like generating the 8 rows to save us some time. All right, so then this is going to be our 3y next to every one of these. Now, what operation is between these is multiplication. Yes, there is a plus between each one of these things, but each term of this, when it's expanded, really has a plus sign. So this is a term, these things are multiplied together, then this is a term because those things will be multiplied together. Now that we've had those, we actually need to put our exponents on this. The highest degree is 5, so our first term in our first term, that first part, will be raised to the 5th power. In the second term, it'll go down 1 to 4, 3, 2, 1, 0. I'm going to cancel this out because I know it means multiplication of 1, and 1 times 1 is 1, so I don't really have to worry about writing that part down. And then from right to left, this will count down. This will be the highest degree on the term that was b, in this case 3y. So 5, 4, 3, 2, 1, 0. Anything to the 0 power is 1, but 1 times 1 is still 1, so I'm just going to leave it like that. Now, before I can actually multiply the 5 with this and this, I need to take the time to raise this to the 4th power, to raise this to the 1st, to raise this to the 3rd, to raise this to the 2nd. And so what that's going to look like will be this. It'll be 1 times 2 to the 5th. I'm going to get out my calculator. I don't really need it. I know 2 to the 5th is 32. But some of them I might not know, and I just want to be real quick. 2 to the 5th is 32. So I have times this red one becomes 32x to the 5th. Now I'm going to have 5 times 2 to the 4th, I know is 16. So this will become 16x to the 4th. So my first step in all of this was to grab row 5 of Pascal's triangle. I wrote down those coefficients that we're going to use as our starting coefficients, the 1, 5, 10, 10, 5, 1. And then I plugged in what a was and what b was next to each one, putting the exponents on a counting down from left to right, on b counting down from right to left. Now, before I actually write my final answer, I'm taking the time to raise this to the 5th power, raise this to the 0, raise this to the 4th power, raise this to the 1st. So there is still a 3y there. Now we have 10. 2 to the 3rd is 8, so this becomes 8x cubed. 3 squared is 9, so that becomes 9y squared. Plus 10. 2 squared is 4, so that becomes 4x squared. 3 cubed is 27, so that becomes 27y cubed. 2 times x to the 1st is still going to be 2x. 3 to the 4th is 81, so this becomes 81y to the 4th. And lastly, we have 1, and that's 1. 1 times 1 is 1. 3 to the 5th, I should know this, but I don't. So I'm going to put it in. 3 to the 5th is 243. So 243, that's going to be 1 times 243y to the 5th. So I've gone through and actually taken care of my exponents on each piece and actually raised this to the 5th power. So now I can actually multiply everything that's together in a term. Well, in this term, it's just that times 1. So my final answer for this part is 32x to the 5th. Here I have 5 times 16 times 3, which is 240. So plus 240 x to the 4th y to the 1st. Now I'm going to put those in. I have 10 times 8 times 9, which is 720, x cubed y to the 2nd. Here I have 10 times 4 times 27, which is 1080, x squared y cubed. Here I have 5 times 2 times 81, which is 810, xy to the 4th. And lastly, we have 1 times 243, y to the 5th. This is our final expansion. This is what we would get. This is the answer to this binomial raised to the 5th power. So rather than writing out 2x plus 3y, by 2x plus 3y and finding that product and then multiplying by 2x plus 3y and doing this until I've had 5 factors of it, which will open me up to lots of room for calculation errors. I can use Pascal's triangle to generate the lead coefficients, my starting coefficients. Okay, if the coefficients are 1, those will actually be the final coefficients, but if the coefficients aren't 1, that's not going to happen. And then I can go down from left to right on degree and from right to left for the second term of that binomial. Actually take the time to raise them to the power to make sure I get the right value of 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st, 3 to the 0, 3 to the 1st, 3 squared, and make sure we put the exponents correctly on the variables as well. And when I'm done, I should see that 5, 4, 3, 2, 1, 0 x's, 5, 4, 3, 2, 1, 0 y's with these numbers that we calculated. So this is our final answer. I'm going to ask you to pause the video a moment, but we're going to change this problem first to 4x minus 3. 4x minus 3 to the 6th, which means it's actually going to be treated as 4x plus negative 3 to the 6th power. Our a in this case is 4x. Our b is negative 3. Go ahead and pause the video for a moment and see if you can expand this to what you should get when you expand it. I don't want you to do anything else but write out the lead coefficients and write down what goes next to them for now. All right, welcome back. And so here is what you should have. You should have started with row 6 of Pascal's triangle, which is 1, 6, 15, 20, 15, 6, 1. I have those there in blue. Then the first term, our a, is 4x, so I put that in parentheses next to each one of those starting coefficients. And I counted down from the power of 6, 5, 4, 3, 2, 1, 0, crossed out the 0 term. And then I wrote down the second term of negative 3 next to each one. Next to every single one, I put a negative 3, and I counted down from right to left. 6, 5, 4, 3, 2, 1, 0. Obviously, the 0 term is a 1. Negative 3 to the 0 is 1, and 4x to the 0 is 1. But because they're multiplied by 1, I just crossed them out instead of putting a 1 there. So now I'm going to go through and take care of my exponents. So I have 4 to the 6th power, and I'll have 4 to the 5th power, and 4 to the 4th, and so on. So this is actually going to be 1 times 4096 x to the 6th. Remembering that our negative 3 went away, I'm not going to worry about that. Plus 6 times 4 to the 5th is 1024 x to the 5th. Now, if you want, you can simultaneously do your other term. For some of you, it might be better just to do the first terms first, counting down, and then the second, but you got to make sure you leave enough space. I'm going to do this simultaneously. So I have this is negative 3 to the 1st, which is just negative 3. And my next term, I have 4 to the 4th, which is 256. So this red term becomes, oh, I can't forget the 15 that's in front. There's a 15 in front, and then a 256 x to the 4th. And the negative 3 squared becomes positive 9. My next term is a 20, and then 4 cubed, which is 64. So that'll be 64x cubed. And then negative 3 cubed is negative 27. And then I have my 15. Don't forget to put the starting coefficient on. And 4 squared is 16, so this will be 16x squared. Negative 3 to the 4th is positive 81. Our next term is 6 times 6 times 4x, because that's to the first power, negative 3 to the fifth. So I need to do negative 3. I need to also do it in parentheses or it's going to have a problem. So I know it'll be negative, but I just want to show you how to verify. So negative 3 to the fifth power is going to be negative 243. So this right here is negative 243. And then our last one is negative 3 to the sixth. So I'm going to just recopy that and change that exponent to a 6, is 729. This, again, is not our final answer. We were just taking care of the exponents on each part of the term. So now, for each term, we're actually going to multiply this out. So this becomes 4,096x to the sixth plus, for this term, I have to do 6 times 1024 times negative 3. So this is actually going to be minus, because of the negative. I could just do plus negative, or I could write it as minus. I'm going to write it as minus 18,432 x to the fifth. The next one will definitely be a plus, because I have positive times positive times positive. 15 times 256 times 9 is 34,560 x to the fourth, plus 20 times 64 times negative 27 will give us, it'll actually make this a minus because it's a negative. So this will become minus 34,560 x cubed. So 1, 2, 3, 4. Now I'm on to my next term. 15 times 16 times 81, this one's positive 59,535. And that is x squared. And then I have 6 times 4 times 243. It's a negative 243, so that will become a minus 5,832x. And then our last term was just plus 729. So if you look, you can see we have positive, negative, positive, negative, positive, negative, positive, which is what we should see when there is a positive first term and a negative second term in the binomial. This ends this clip. There is going to be a second clip on how to find binomial coefficients.